Hi guys, today's problem is task D of ABC 257. The settings are as follows. We have n trampolines on the XY plane. Each coordinate of the trampolines is XY, XI and YI, and PI is the power of the trampoline. Then we can choose any integer s, and if the inequality is satisfied, then you can move from the ice trampoline to the j's trampoline. For instance, we have the first trampoline whose coordinate is 2, 1 and its power is 1. We have the second trampoline here, uh, whose coordinate is 3, 2, 3, and the power is 1. Power is 3, sorry. Uh, if s is 1, the inequality from the first trampoline to the second trampoline is false, so you can't move from the first to second. But if s is 2, the inequality is satisfied here, and you can move there. On the contrary, you can move from the second to the first in any case, because the power 3 is so strong to move. The problem is to find the minimal value of s to use all the trampolines jumping one after another. But we have no limits for times of jumping, and you can choose any trampoline to jump on first. So you can start any position like here, like here, and then go there, go there, and go there. Then uh, uh, if you want, you can go back to the trampolines you used before. So the settings are very complicated, but note that uh, n the trump the number of trampolines n is very small, uh, which means n is less than 200. This is a very important constraint. So let's talk about the solution. First, characters in the inequality are almost all fixed. But s is only unknown variable. So solve it for s, and using the sale function here, then we get the minimal power to move from I to j. Then we can forget the coordinate xi comma yi and the trampoline power. We can forget them and we only remember these minimal powers. Then, as a graph problem, we get the directed edge from I to j, whose weight is this. Then you may ask how much power we need to move from I to j because you want to know the minimal value of them. If the graph is like this, you can calculate the power from I to j is like this. Maximal of 5 and 3, and we compare these two, and then we choose the minimal one. Then the uh, distance is 5. So interpreting it as a graph problem, you may ask how far it is from I to j. It is the same as this. So the problem is just to compute the minimal distance from I to j. Let's summarize this approach. First, we fix I and this is the start position. Then compute all the distances from I to any vertex. Then choose the maximum value from them and this is the minimal power you need to start from I. So repeat this process for each I. Finally, choose the minimal value uh, that is not maximal. It is a little bit confusing, but uh, then we get the answer. So the last task you must deal with is how to compute the distance. We have two famous algorithms for it, and I introduced them. Uh, One is the Washer-Floyd algorithm, and you can compute the distance from each pair I and j. I is the start position, and j is the uh, end. The other is the Dijkstra algorithm, and you can compute it for fixed I. This is the difference uh, from Washer-Floyd and each j, any j. J uh, Dijkstra is useful if you you only want to know all the distances from one vertex. But in this case, we must know all the distances of the pair ij, so it's better to use Washer-Floyd. So finally, I tell you how the washer fluid works. If you don't know it at all, I recommend it that you should Google it and see the code before watching this section. First, fix a halfway vertex k, which means you must pass k halfway down the path. Then, for each pair ij, compare I to j with I to k to j. If I to k to j is shorter, then note the distance from I to j as the distance of I to k to j. So like this, if you want to know the distance from I to j, compare the distance and choose the minimal one. So remove it. So as a result, we have checked for each pair of I and j whether we should pass k or not. We should pass. So we have checked whether we should pass k halfway down I to j or not. Then repeat the vertex. Then replace the vertex k with another vertex k prime and repeat the process. Then we will find out whether we should pass k prime or not this time. So like this, if k dash k prime here, then we check this I to k to j or I to k to k prime to j. We compare these two, and then choose the minimal one. So I remove the green path. This this path is minimal gives minimal path from I to j. Repeat it for each k, and finally we get the distance from I to j. That's the Washer-Floyd algorithm. That's all about Washer-Floyd, and then that's all about the task D. Uh, Thanks for watching. My code is on the description.